Hi, welcome back. The last video that we viewed, we applied DeMoivre's theorem to find the complex cube roots of negative I. And we understand this is also equivalent to, say, solving this equation over the complex plane. And these are the three roots that we had gotten. And I indicated that you could check those on your calculator. So if you take out your TI-84 and you check the mode key, if you go down almost the last row, if you press the mode key, it says real, and the next thing it says is A plus BI. So I recommend you move over and highlight the A plus BI, and then you can type any of these in and parentheses to the third power, and you will definitely get negative I. I tried it. Okay, now in case you're wondering how do I get the I is in blue above the period key. So you simply type second, the period key, and that would give you the I. Okay, so that works out very nicely, and you can check any of the problems that we do using that method. So let's do another example. It's going to be sort of similar. So let us, here we go, clean this up. All right, so our second example of DeMoivre's theorem in finding roots or solutions of equations would be right off of our worksheet, complex numbers in the polar form DeMoivre's theorem exercises. We're going to do 7D, which says to find the complex roots of 8I. Okay, and I hope you understand that that would be equivalent to solving the equation x cubed minus 8I equals 0, because if we moved it over, then we would get x cubed equals 8I, and we'd be looking for the cube roots of 8I. Okay, so what we're going to do is we're going to start by writing 8I in polar complex form. Okay, so 8I, as you can see, would be right here. Okay, and the R value would be 8, of course, and the angle would be 90 degrees. So this would be 8 cis 90 degrees. So what we're going to do, we're going to write that at 8 cis 90, and then we're going to apply DeMoivre's theorem, which says that the cube root, okay, is going, well, let me write it down here. Well, actually, the nth root would be, we take the R value, the nth root of the R value, and then we do cis, and we take the actual value of theta, or starting value of theta, we divide by n, and we add increments of 360 over n, and k is going to go from 0 to n minus 1. So we're going to get n roots. So if we're doing a cube root, we're going to get 3 cube roots. Okay, so here we go. We start out, and whether we use x or z, it really, I guess in this case, it doesn't matter. Okay, we start out with the cube root of 8, which is 2. And we take 1/3 of this, we divide this by 3. So it's going to be 2 cis 30. And that will be the first of our cube roots. And to get the next one, we take 360 divided by 3, and we're going to add 120 onto our 30-degree angle. So the next one, 120 plus 30 is 150. And the next one, add 120 again, is 270. So these are our 3 cube roots of 8 cis 90, which is equivalent to our 8i. Okay, now one helpful thing that you want to see is that these 3 roots are spaced out on a circle in the complex plane with a radius of 2, and they're equally spaced. So let me see if I could draw a picture of that for you to help you understand what is going on. Okay, so let's see. So what we're going to do here is we're going to picture the complex plane, and we have one root at 30 degrees. We have another root at 150 degrees, and we have another root at 270. And these 3 roots are equally spaced 2 units away from the pole at 30 degrees, 150 degrees, and 270. So there definitely is a geometric aspect of these problems. Okay, so this would be 2 cosine of 30 is rad 3 over 2. And the sine of 30 is 1/2. And when we multiply by 2, we get radical 3 plus I. So this will be 1 of our cube roots. And then we continue on. We picture 150 degrees and the cosine there. Well, all right, let's make a quick little sketch. 150 would be right here. And 1, 2, and this would be negative radical 3, right? So the cosine 150 is negative radical 3 over 2. And the sine, of course, is positive 1/2. All right, put the I back in front, it really doesn't matter. So this gives us negative rad 3 plus I as a second root. And as our third root, well, this is a little bit easier now. It's a quadrantal angle that's at 270. Okay, and that's simply, what is this? The cosine of 270 is 0, and the sine of 270 is negative 1. So this would be 0 minus 1i, and when the smoke clears, you get negative 2i. So we get these as the 3 complex roots, complex cube roots of 8i, and we get these as the 3 roots of that equation. Okay, so we'll do one more example, and at this point, you should be able to do virtually any of the problems on this worksheet, and you should try to do a representative sampling. I'm going to now do question 8E. So let me pause this so I can erase. Okay, so we resume with question 8E, and 8E wants us to solve x to the 6th plus 64 equals 0. Now, fundamental theorem of algebra says 6th degree, 6 roots, not necessarily the same, but they will be 6 distinct roots in the complex plane. So in other words, x to the sixth is negative 64. So x would be the sixth roots, the sixth roots of negative 64. Okay, so if we picture negative 64 is a real number. The sixth root isn't, but negative 64 is. And it's clearly theta would be 180 degrees. So therefore, negative 64 equals 64 cis 180. So we're going out 64 units in this direction, and that direction would be 180 degrees. Okay, so this is what we'll be taking the sixth root of. You can call that z, you can call it x. It really doesn't matter. Okay, so let's get the sixth roots of 64 cis 180, which we know equals negative 64, and that would solve our equation. Okay, so let's go through this step by step. The first one, well, the rule is we take the sixth root of 64 and we divide this by 6. Okay, so the sixth root of 64 is 2, because 2 to the 6th is 64. So we're going to get 2. I'm going to move this over to make sure I'm going to have room here. Okay, so we get the first one is going to be 2 cis, divide this by 6, 30 degrees. So that will be our first root. And then the idea is the 6 roots are going to be equally spaced around the 360 degrees of a full circle. So if we take 360, divide by 6, we get 60 degrees. So every 60 degrees, we're going to get a new root. So I add 60 onto this, 2 cis 90. That would be my second root. I add 60 onto this, 2 cis 150. I add 60 onto this, 2 cis 210. I add 60 onto this, 2 cis 270. And finally, 1, 2, 3, 4, 5, 6. I add 60 onto this for 2 cis 330. Okay, so those are the 6 roots. And all we're going to do now is we're going to do some arithmetic on them, and we're going to try to change them into a plus bi form. Okay, so you've done this enough times, you should be fairly good at it. Okay, cosine 30, rad 3 over 2. Sine of 30 is 1/2. You multiply that out, you get rad 3 plus I. And that will be the first of our roots in a plus bi form. Okay, 90 degrees is a quadrantal angle. Okay, so we know it's just I, so 2 times that would give us 2I. Okay, because it's right on the I axis. Okay, 150. Well, that's in quadrant 2, of course, and if we were to make a brief sketch, okay, we would have that diagram, and cosine is negative rad 3 over 2. Well, it's just 2 times I, okay? This would be negative rad 3 over 2. And the sine of 150, as you can see, is a 1/2. See, this is our 30. Okay, so that would be positive 1/2. And when you multiply by 2, we get negative rad 3 plus I. Okay, and the next one, 210. Well, we've done these many times, so we know we are in quadrant 3 for that. And 210 gives us a reference angle of 30. Okay, so let's see, cosine of 30, adjacent to our pi, rad 3 over 2. Okay, and then the sine of 210, opposite of our hypotenuse is negative a half. Multiply it out, rad 3 minus I. Okay, so not the same, they're close, they are going to be distinct. And 270, well, that's right down here, so that would be minus I. So 2 times negative I, negative 2I. Okay. And last but not least is 330. So that would be right here, 330. 1, 2, radical 3. And of course, that's a negative because of its orientation. And cosine of 330, rad 3 over 2. And sine would be negative a half. With the I, and multiplying it out, you get rad 3 minus I. Okay, so these are your 6 complex roots of negative 64, and that would be the 6 solutions to this equation as told by the fundamental theorem of algebra, and we've used the last part of DeMoivre's theorem. Okay, so I recommend to you to do as many problems as you can on that worksheet, and there's a couple pages of solutions. I worked them out step by step, every single one. So this should be something that you can have some success with. And there will be a take-home which will involve polar graphing and DeMoivre's theorem, and that will be posted up, and there will be a due date with that, and you would have to submit that via email in PDF format, and that will be part of our grade. Okay, thank you.